Welcome to the sky at night. This has been a most exciting period. Exactly on schedule, the probe at deep impact collided with comet Tempel 1. Mind you, the comet is avocado-shaped, only about 6 miles long. It was 83 million miles away. That was an amazing feat of navigation. We didn't know what was going to happen. Well, one of the main centers of observation was Palomar Observatory in California, and Chris Lintott was there.
I'm standing outside the dome of one of the world's great observatories, the Palomar 200-inch. The world's media are just down the road at Mission Control, but we wanted to be somewhere where we could see the night sky for ourselves and observe the impact. Although space-based observatories like the Hubble Space Telescope will be looking, large ground-based telescopes like this one have a lot to contribute to the exciting story that's about to unfold. The massive telescope is an imposing presence in its giant dome, constructed in the 1930s and completed in 1948. Built by solar astronomer George Ellery Hale to attempt to determine the fate of the universe, it also ranks among its many achievements the discovery of the first quasars in the 1960s. For the last few nights, it has been observing the comet in the infrared and will do the same tonight for up to an hour when the comet will set. The infrared camera is cooled to extremely low temperatures using liquid nitrogen, and this should allow it to detect the heat released as the impacting spacecraft is vaporized. British astronomer Richard Ellis is in charge of Caltech's observatories, which includes not just Palomar, but the twin 10-metre Keck telescopes in Hawaii, which also hope to observe the impact. So thank you for the invitation, and Palomar is a fabulous sight.
Well, welcome, Chris. Yeah, here you see the famous 200-inch, and we're going to be having an exciting time later this evening looking at comet Tempel 1 and the deep impact into that comet. Hopefully something exciting will happen. It looks like a great night. The weather looks fantastic. Of course, the 200 inch is a very historic and famous telescope, but this is a very good example of how we're still using it every night to do world-beating science. There are many other telescopes here too, including the 48-inch Schmidt, which of course did the famous sky survey, 60-inch, which we've automated and is using to study gamma ray bursts. And we have a partnership here between the 200-inch telescope and the twin Keck telescopes in Hawaii, which Caltech owns and operates as well. So this is still a forefront observatory, and welcome, and well, hope we'll have some exciting times tonight.
Well, fingers crossed, and all we can do now is wait and see what's going to happen.
Absolutely.
The dome is kept at nighttime temperatures throughout, isolated from the hot Californian summer, so observations can start as soon as the dome is opened. It's now sunset, and the telescope rotates to focus on the comet, its only target for the next few hours. Standing inside the dome, the motion is incredibly smooth. It's difficult to believe that when the mechanism was built, welding it together was an innovative and risky new technique. The observers in charge tonight are James Bauer and Bidushi Bhattacharya. So in the control room, a few hours before impact, how does it feel?
Anxious, very anxious. We're, hoping for a very spectacular event tonight. So yeah. I think.
And it's one of those amazing times in astronomy. We've no idea what's going to happen.
That's right. That's right. There are predictions that range from very subtle effects to extreme brightenings of several magnitudes.
It's 10:52 local time. Mm-hmm. The impact happens. What are you doing at that moment?
At that very moment, we're going to be staring very closely at the computer. We have a set of exposures that we're going to take. We don't know how bright it's going to be when the comet hits. So we've got contingency plans. We don't want to have it be so bright that the instrument actually saturates.
Now the unfair question, what do you personally expect to happen?
I think that the asteroid will the nucleus of the comet is probably harder than people think. There are some theories out there that it's a loose rubble pack. But I have the sense that maybe it might be a little bit harder so that the impact particles that come off will not be small things but bigger bits. We don't know. It's going to be great.
The comet's about as close as it ever gets to Earth, which puts it just about in binocular range and perfect for large amateur telescopes. In fact, NASA have been using amateur observations to monitor the progress of the comet over the last few months and even to target the spacecraft onto the nucleus. I've come out to join some fantastically well-equipped local amateurs. Well, you've got a reasonably large telescope here. What is that, a 12-inch?
That's a 20-inch.
Oh, okay, fine. There goes my estimation.
Well, you need all the aperture you can when you're looking for something as faint as this.
And have you seen the comet through it already?
Yes.
And what does it look like?
Very faint, fuzzy ball.
Okay, so a faint comet, in other words.
Yes. Yes.
I'll be using this CCD camera to try to capture images of the comet, just before impact and afterwards, to see if I can capture some of the, brightness increase.
Have you already managed to get images of the comet?
Not yet, no.
Okay. And so when it comes to the comet, are you imaging it or just looking visually?
No, I'm just looking visually tonight. Just hope to see it that way.
A giant telescope like this collects enough light to see incredibly faint objects, but the effect of the Earth's atmosphere means that its resolution will be no better than that of a large amateur telescope. To solve this problem, astronomers are developing what are known as adaptive optics. By monitoring the behavior of the atmosphere and adjusting a mirror accordingly, they can remove the worst of the problems and effectively put the 200-inch in space. Well, Richard, it's a beautiful night outside.
Yeah,
how's the telescope doing?
Yeah, we're really lucky. It's a truly spectacular night. It's half arc-second seeing. That's the width of a star image here in the infrared, and that's extraordinarily good. And Dr. Bauer and his team are using a very clever technique, adaptive optics, to remove the blurring in the atmosphere. This hopefully will bring the images down to about maybe 0.3 arc-seconds. Well, that's pretty amazing. That's only a little bit worse than Hubble Space Telescope.
You're effectively putting the telescope in space.
Yes,
You're getting rid of the atmosphere.
That's exactly right, yeah.
Now, I know you normally observe galaxies, but how are the images of the comet looking?
Okay, well, they're really very good. The comet is, of course, very, very bright compared to a galaxy, so we're looking at detail here, and the images, of course, need to be processed, but spectacular stuff is coming in.
And it's just the beginning.
And it's just the beginning, yeah.
What we're doing right now is I'm just getting set up on the comet, and I'm finding some guide stars, which I'll set up in the computer. And once I have the guide stars, I'll start tracking those stars and hopefully start to integrate images of the comet.
We're looking at a video image of the comet that is going to be impacted in just a couple of minutes. The image is being updated every 8.5 seconds or so, and it's right in the center of the field.
It's very faint, very dim, but it's definitely there. And hopefully it'll get a whole lot less dim in a couple of minutes.
Amazingly, we're seeing this sharp image of the nucleus, and you can see structure in it. There's clearly knots and holes on the side.
There's a crater there already.
Yeah, it's amazing. Yeah, it's almost as if somebody's been there already. Yeah, incredible. So, and here at Palomar, we're locked onto the comet now, and we're monitoring its brightness.
Okay, we have 30 seconds.
30 seconds.
What do you guys think?
We have a hit.
Whoa, it's getting brighter.
About 20 seconds before NASA were due to hit the comet, the telescope here saw a dramatic brightening in the comet. I think the observers from around the world are calling in now, and the comet doubled in brightness. We think we saw a jet, and we're just now receiving from NASA the first images of the site. Looks like we hit the southern end of the comet, near the edge, and now we wait to analyze the results.
Inside the comet, it looks more stellar, which means that it looks like a
White spot.
a white spot in the middle.
It looks like something has sparked it up.
Well, it's still very faint, but the center
It's gotten brighter.
seems just a tad brighter. It's hard to tell if that's due to just dark adaptation in our eyes, making it easier for us to see the core of the comet, or whether we're really seeing a true effect.
If that's really happening, that is quite exciting.
It could just be wishful thinking, though, unfortunately.
I think it's definitely brighter.
Yeah, it looks brighter to me, too.
How bright is it now?
Probably about 5 times. About 5 times. But that's through increasing air mass. We're tracking it pretty low now.
In other words, it's dropping lower and lower to the horizon.
That's right. That's right. Lower and lower altitude.
We had a comparison star next to the comet, and that comparison star was brighter than the comet. After impact, or after the time of impact, we could see that the core of the comet was brighter than the comparison star. So that's great.
Yeah.
Yep. And this is the guy that did it. So
You did it now.
you did it.
It certainly does look like the impactor did hit the comet. The comet did become noticeably brighter. I can't wait to see what's been observed at Keck and Palomar and Hubble.
The images are being processed behind me, and meanwhile the flyby probe is sending back the images it received from the impactor, and it will continue to do so for about 13 minutes after the impact, and then it has to pull back its shields to pass through its close approach to the comet. Hopefully we'll recover it on the other side, but if not, we've got these 13 minutes of data which are now coming down, and they are spectacular.
Oh, this is awesome. We are so psyched.
It's wonderful.
Yeah.
Wonderful and still a little anxious because we have to reduce it all and analyze it all.
Yeah.
Of course.
An amazing event here, looking at the comet, seeing it brighten up. But now that it's starting to set at this time, and so we're saying goodbye to the comet. But we're up here at Palomar. It's New Moon weekend. It's absolutely fantastic.
And now we're just going to enjoy the rest of the evening with our telescopes, great weather, and at the very historic Palomar Observatory.
It's 1 in the morning. The comet's now set from Palomar. And I can't help wondering what Temple, who discovered the comet back in 1859, would have made of the amazing images that we've seen tonight. Whatever he would have thought, there's lots more still to come.
Well, that was a great moment. Welcome now to our two distinguished guests, Professor Iwan Williams and Dr. Andrew Coates.
Hello.
First of all, Iwan, can you take us through the sequence of events?
Yes, well, as you know, there's the spacecraft was made up of two parts. There was the impactor and the flyby. And a few days ago, the impactor was ejected from the flyby craft and targeted towards the comet. And the sequence we see is from the camera on the impactor as it closes in on the comet nucleus itself. It starts off obviously far away, and very excitingly it finishes within a few seconds almost of when it's self-destructed on the nucleus. It's very interesting to see the navigation as the impactor closes in. We can see the odd few corrections taking place as the nucleus sort of bobs about a bit. It's not really the nucleus that's bobbing about a bit, it's the spacecraft correcting itself. And as we see in the images here, fantastic sights of a comet nucleus, which we really have never seen in such great detail before. The mission was almost worth it just for these close-up pictures of a comet's nucleus. We see a fantastic crater, we see cracks, we see all sorts of geological features, which was very exciting and we've never seen before.
Was that what you expected, Andrew?
Well, I don't think we knew what to expect, really. The closest we've ever been to a comet, the best pictures we've ever had, and so to actually see craters down to the smallest scale, I think this was something of a surprise, actually, and it tells us something about the surface. It tells us that the surface might actually be sort of relatively hard, the outer crustal layer, and then this was very important for interpreting the way that the impact and the ejector actually happened later on. There was a wonderful sequence of images shown just as the impactor actually went in. We saw the flash associated with the impact and then a shell of gas or dust actually expanding away from the impact site. And this casts a shadow on the cometary nucleus. You can see that actually behind where the impact has actually happened. You can see it expanding with time, getting bigger and bigger. So this is the first part of the plume actually coming away from the impact site. So a very dramatic sequence of images.
What are the main materials of the comet?
We used to think, following Whipple, that of course a comet was
a dirty
snowball.
Yes,
in other words, mostly water, ice, other ices, with little bits of dirt thrown in. I think one of the things that Deep Impact has told us, and I'm sure we'll come back as the story unfolds, is that this comet certainly had much more dust in than we expected. We see it in these fantastic details in the craters. This requires a strong surface, which suggests much more dust rather than ice.
There are other types of ices as well. So there's things like carbon dioxide, which turns up in the spectra that we see from the various observatories. There's ammonia. There's other types of hydrocarbons as well. In fact, there's more complex hydrocarbons, for example, methanol. And in addition to that, there are small amounts of silicates in comets also.
Before the impact, we were talking about this, you may remember, and we didn't know then whether the impact would make a crater or would simply disappear, or what would happen. Well, the impact was about the size of a washing machine. It had no explosive, of course. It was merely a solid thing that hit. And, well, what did we see eventually?
I think everyone was surprised by the amount of material which actually came away from this impact. It really brightened up considerably. And so that's seen in the images seen from the flyby spacecraft, where we can see not only the nucleus itself, but also beautiful structure of the stuff which is actually coming out. Now, we haven't seen the crater yet. It hasn't been possible to actually process the images and see the crater, but there must be a crater. So the impactor will have gone through the relatively hard surface into the interior and caused a huge explosion, which has brought lots of dust in particular out, but also presumably some gas as well, although it's difficult to actually see the gas. It's mainly dust, and so what we see mainly is to do with the sunlight reflecting off the dust.
I wonder if we will. After all, telescopes all over the world were looking at the comet, and also the various spacecraft.
Yes, there was from space, both Rosetta and Hubble took images. Professional astronomers were involved. We've already heard a bit about the Palomar results. And amateurs, including a group of school children who were involved in doing remote observing from Hawaii using the Folks telescope. And important to say, they were actually the first to get online a picture of the brightening of the comet following the flash. So congratulations to everybody involved in these observations.
What about the famous Hubble Space Telescope? That must have been very much on the alert.
Yes, this showed some fantastic images. In fact, all the world's great observatories in space were watching it, and Hubble, of course, was there too. And this showed an image where one can see a fan of material actually coming away from the comet somewhat after the impact. I think one of the surprises with the Hubble images is that the main part of the fan is something like an hour after the impact itself. But there were many other space observatories looking at it too, and one of those in particular is the Swift satellite.
What's Swift intended to do?
Yeah, Swift is designed to look at gamma-ray bursts, so these are the most powerful explosions in the universe. And in this case, it was actually turned round to look at a relatively small explosion, but within our own solar system. And so this got some wonderful results as well. In fact, there was a sequence of images taken before impact, which showed the optical and ultraviolet light response and how that changed. So one can see the comet moving across the sky with respect to the fixed stars. And then if we look at the amount of light which is actually coming away from the impact, we can see that increases significantly. It's a large factor. It's at least a factor 4 and possibly even more than that. And then this decays, and then even as of about 24 hours, 48 hours after the event, it was still about 30% brighter than it was before. So it's a sustained increase in brightness of the comet.
Well, that won't last. After all, we've got to remember two things, I think. First of all, the comet itself is completely unfazed. That will go on going around the sun quite happily. Indeed. And secondly, there was absolutely no danger to the Earth or anything else. I think that's important to make that point.
Well, there never was, because this particular comet never really gets closer to the Earth than the orbit of Mars. It orbits between Mars and Jupiter. So even if we had an impactor the same size as the comet, it would be hard-pressed to get this comet to hit the Earth.
It couldn't disturb the orbit at all?
Not really, no. As people have said, it's like a washing machine landing on the Isle of Wight or something.
Exactly. Of course, there were amateurs too. John Fletcher got a nice photograph from here in Gloucester. There are plenty of amateur pictures.
Yes, the amateur pictures really add to what we can get from the professional observatories and give a sense of context for what we actually see. So I think this has been, also one of the spectacular things. I mean, telescopes around the world, both professional and amateur, and of course the space observatories, all of these were looking at this event. It was an event which really united the astronomical community together in looking at this particular event. And we're still going through it. We still actually have observations going on right now.
We've now seen 4 comet nuclei, and they've all been different.
They have, yes. Halley was the first we saw through Giotto. That was quite far away. The general shape of Halley was very similar to the general shape of Tempel 1, but we did not get any real resolution of the surface at all, only some inference. Then came Borelli, again long and thin, some interesting surface features, but nothing like the surface features we've got on Tempel 1. And then Wild was also more round, not quite as exciting, I would say, Andrew.
Yeah, I think one thing which sort of links them all is that the surfaces were actually extremely dark, and with the Halley results from Giotto, this was the first big surprise about comets. And of course that crust is left over as material from the interior, basically moves away from the comet. As the comet comes into the inner solar system and warms up, we lose volatile material. So all of the 3 comets we've seen so far are really very dark, and this is one of the distinguishing features. And that's the case also with Tempel 1. So we have this crust which surrounds the nucleus, relatively strong, it seems, according to the deep impact results. And we have the material inside the cometary crust, which is pristine material left over from the beginning of the solar system. And then moving outwards from the cometary nucleus, we have the material which evaporates away, so gas and dust, which come away from the cometary nucleus, and that's the cometary coma. And then outside of that, comets actually have two tails. So they have a tail to do with dust and a tail to do with gas or plasma. So that's the sort of general features of a comet. What we saw with Comet Tempel 1 was, in fact, of course, the cometary nucleus was the star of the show, but we also saw the cometary coma, the neutral material, principally dust, but with some gas as well. This particular comet didn't have tails.
One thing important, I think, comets are very ancient things. They go back to the formation of the solar system.
Yes, they were formed at the same time as the solar system formed. One can also sort of simply think of the formation process in the solar system as small lumps, very, very small lumps beginning to stick together in the solar nebula, accumulating, getting bigger and bigger up to planetesimals. Near the Sun, in the terrestrial planet region, we have this happening with rocky material only, and this gives us the rocky planets, finishing up with the asteroids. When we move further out, water also condenses, the same process of these solids sticking together, but this is probably now dominated by water ice. So we get bigger things, the planets outer Uranus, the trans-Neptunians, and of course the cometary nuclei, all forming through this accumulation process at the same time. So it's very important to look at a comet because they have been out there. They have not been altered like the planets have by any evolutionary process. So when we look at a comet, when you look at the cometary interior, we really are seeing the building blocks of the solar system.
What about you, Andy? What do you think are the most important results?
Yes, I think there are many hugely important results. First of all, it's telling us about how cratering actually works. And so this, the very experiment, the sort of audacious experiment really of putting an impactor into a comet and seeing what happened is telling us about cratering. So it's telling us about the surface of comets. The surface of comets is left over from when volatiles actually escape away from the cometary nucleus. So we can tell things about the strength and structure of that. We can also look underneath the surface and look at composition. So in fact we were lucky enough to do some spectroscopic type of observations from the UK Schmidt telescope in Australia. These tell us about how the comet brightens both in terms of the dust and in terms of the gas. So we can look at the continuum, which is the light over all wavelengths, tells us that basically the dust increased by quite a large factor, at least a factor 4. And then we can look at the way that the different species in the cometary coma, the way those compare to each other, both before, during and after the impact. And those will be telling us about the composition of the pristine material underneath the cometary surface.
It will be interesting to look at the comet in a few months, few years' time. My guess is it will be totally unchanged. What do you think on that?
Well, certainly some of the images we've seen already shows that the basic shape of the coma is the same as the basic shape before. Our artificial impactor has generated the same thing as nature does by itself, by and large. It's formed, it seems to be following the same physics, which makes it very important because it's telling us that everything we learn from this artificial impact will also be true about the natural formation of jets, natural formation of cometary tails, etc.
After all, comets like that are being bombarded by meteoroids all the time.
Yeah, so collisions are very important in the solar system, and the fact that we see craters on this comet down to the smallest scale is certainly real evidence of that. And I think the other thing is that looking at the coma sort of just before and just after, as Iwan says, it's basically on the broad scale, it looks remarkably similar. We did some observations from the Isaac Newton Telescope with Steve Lowry of the Queen's University Belfast actually doing the observations. And these showed some how the coma basically didn't change from before and after the impact. Of course, the intensity changed, but the basic shape of it was similar. However, we did see jet structure which actually did change. In fact, there's one jet which appears to be in sunlight just before the encounter, and then that basically is extinguished because the comet rotates. But then there's new jet structure which appears, which is actually to do with the impact itself. So these results are going to be very important in understanding the shape of what we're actually seeing. So wonderful results, and all of these telescopes are providing interesting data.
What do you expect during the next few days?
During the next few days, I think there's a chance that that we might start seeing some gas. I think, as we said before, one of the surprises was that really this looks a very dusty type of encounter. There hasn't been much gas. Now, if gas is produced in significant quantities, that will then start interacting with the solar wind. We may see effects in the plasma tail. None of this has been seen yet at all. And then there's the possibility of actually X-rays actually coming from the cometary region, because if we have neutral gas in the solar wind, we know from other comets, from recent results, that as the solar wind ploughs into the cometary environment, it actually produces X-rays. No significant X-ray intensification has actually been seen yet, but in the next few days there's a chance that we will start seeing that. So the observatories will keep looking at it. It's very important with this event to see the before, the during and the after, and to keep observing after. And this is why the space and ground-based campaign has been so important, to actually get that coordinated.
Certainly amateurs can go on observing it. There's quite near the star Spica in Virgo, so it should be fairly easy to find. And what telescopes are needed? Would binoculars show it now, do you think? Maybe you've got 7 or 8?
May just about be becoming visible with binoculars, but I think, you know, overall the event is now sort of appears to be tailing off. But if the plasma interactions do start, then certainly it will be worth looking at that again. But now it's about 30% up on its pre-impact level, which is really not very much. So really, it's a telescopic object.
We now know the results of deep impact. How will this affect our views about future missions?
Well, there are 2 future missions. First of all, the Stardust, which has already flown past its comet. It flew past Comet Vil 2, took interesting pictures, looks different to Comet Tempel 1, but it also flew through the cometary environment and caught bits of the dust from the comet. So it will bring those back to Earth. It's actually doing that next year. So it will parachute those samples back to the planet, so we can look at the composition of the cometary dust. And in addition, the second mission is Rosetta.
And Rosetta?
Rosetta is a marvellous European mission. In 2014, a lander is going to be released to land on the surface, and therefore the results from the deep impact experiment about the strength of the surface, for example, is very important. One now has more confidence that the Rosetta lander will actually be able to hook onto or harpoon onto the surface and stay there. One of the things we have on Rosetta is a penetrating radar which will go all the way through the nucleus out the other side and really will tell us what's deep inside a cometary nucleus.
You know, it would be very interesting to send a flyby probe to Tempel 1 and have a look in a few years' time. I wonder if that'll be done.
Well, a follow-up experiment would be interesting to do, because of course with the new vent which has been created and the crater, it will be interesting to look if that sort of stays there or if it freezes over again, because of course comets are so cold that is a possibility. We may find that out remotely in the next few days if the cometary activity continues to decrease. But yes, ultimately a flyby would be great to do.
Well, it's been a great moment. Iwan, Andrew, thank you very much.
Thank you.
When I come back next month, we'll turn to something rather different. Is there life out there? What about life in the universe? So until then, good night.